Section 4.5 is going to finish up our last section of material about integration for this semester. We do have 2 more sections of material we're going to cover, but they are back in chapters 2 and 3, which means they won't be about integration. So a reminder about derivatives first. If we were looking at the function y equals sine of x cubed minus 4x, and we wanted to take its derivative, what property or rule would we need to use? The chain rule. And what would the derivative be? Okay, so the cosine of what's inside already, x cubed minus 4x. And then what, Jewel?
And then 3x squared minus 4.
Excellent. Okay, everybody good with that so far? Okay, that's what the derivative would be. What we're going to be considering in this class is going in reverse. So taking something that looks like the part that's currently underlined on my screen and going backwards to figure out where it came from. Now, the reason that that's challenging is because what it looks like, the part that's underlined, is a product, right? So we are going to explore at least one way that sometimes products can be reversed to get the original function. This is just one way, and not all products can be reversed like this. But obviously the ones in this section either can, and you'll be able to do so, or they can't, and you'll simply have to say it's not possible. Okay? You'll also see some options, I think, that show up in this section where you can still use some algebra to simplify things, kind of like you did on your gateway possibilities. You may see some of that as well. But we're going to be working backwards. So one option we're presented with finding an antiderivative that looks like a product is to decide if there's a composite function present for which the inside function's derivative is one of the factors being multiplied. So what that just said is that the inside function here has its derivative out here. That's the key. If that's what's happening, then we're able to use integration by substitution, which is what we're seeing in this section. If the inside function, the part that's circled, has its derivative as a product on the outside. So if we consider y prime above, that x cubed minus 4x as an inside function and its derivative 3x squared minus 4 as one of the factors being multiplied, we can let u equal the x cubed minus 4x, and then its derivative, and I know that this is not notation we use all the time, but you'll see why we need it in a moment, du dx, would be 3x squared minus 4, or we're going to rewrite that as du equals 3x squared minus 4 dx. And if you think about it, I'll put parentheses here just to be real clear. We're multiplying the dx to the other side. That's what you're seeing happening in that last step there. So here's the way that this looks. We would start out with an antiderivative that would say cosine of x cubed minus 4x times 3x squared minus 4 dx. And we would identify that this piece is u and this piece is du. And the way that we typically do it is not with this underlined red like I do. We usually write it out to the side. We say, okay, u equals, and it's the inside function, it's the x cubed minus 4x. And then the derivative of u, that is du, equals 3x squared minus 4 dx with respect to x. So I tend to jump over writing the du dx equals out and then moving the dx to the other side and simply go to that specific spot. If that's frustrating to you, then feel free to do it in 2 steps so that you can see those pieces shifting around. And then what we do is we actually replace the pieces that are here. Cosine doesn't have anything to do with the substitution, but the x cubed minus 4x is now the u that I've identified. And everything, the 3x squared minus 4 dx, is the du that I've identified. And the reason that this is nice is because it takes something back to a very simple antiderivative to find. So what is the antiderivative of cosine of u? Sine u. I know we do still need a plus c. I know we haven't seen those in a little bit because we've been doing some definite integrals with some evaluation. But these don't have definite integral notation, at least on this one doesn't. So we're going to put the plus c. And then we always need to make sure that the answer is in the same variable we started with. This problem started with variable x. Right now I've still got the variable u involved. I need to replace the u with what u is equal to. U is equal to x cubed minus 4x. And if you take a look at this, with the exception of the c part at the beginning, at the end rather, it's exactly like what we had at the beginning right here. Right? We've successfully undone the derivative process. So that's going to be what we're going to be looking for today. We're looking for these embedded inside functions where their derivative is on the outside, or at least it's almost their derivative on the outside, and you'll see what I mean by that as we encounter them. So we'll start out with problem 1. Find the indefinite integral. And what we want to see, first of all, is, yeah, it looks like a product, right? I have two pieces that are being multiplied, so it sort of fits in this genre of types of functions. Do you see one function that looks like it's embedded inside of another function? You should. It's the part, I'm going to use, we'll use a blue highlighter today. It's this part right here. It's embedded, it's a polynomial that's embedded inside of a radical. So if we took the derivative of that piece, what would we get? The negative 8x that's on the outside, right? So it's exactly the format that we're looking for. So what we write on the outside is that u is equal to 3 minus 4x squared. Du is equal to, and we take the derivative. That's negative 8x dx. So a word of caution, we are working with antiderivatives and derivatives at the exact same time, right? So be really careful. Go a little slow as you get started with doing this because you're working in both directions within the same problem, and that can make things a little bit confusing. So as we look back at what we originally had, the cube root's still there. The part that's in blue is what I identified as u. And the part that's in red, plus the dx at the end, is what I've identified as du. Or if you prefer, we can write this as u to the 1/3. So what is the antiderivative of u to the 1/3? Okay, so it's u to the 4/3 divided by 4/3, which is the same as multiplying by 3/4. I'll do it in just a second. And I need my plus c. So there's that 3/4. It started out as a cube root, so I'll put my cube root back in. Cube root of u to the 4th. I can't leave the u in. That's a non-optional thing to fix at this point. So my 3/4, my cube root, u is, what was it, 3 minus 4x squared to the 4th plus c. You could leave it like that. That's okay. It's a little bit not friendly that there's 4 of these underneath with a cube root right here. But pulling it out makes it look kind of worse. So if you left it there, I'd be okay with that, and I'm sure WebAssign would as well. If you were looking at, say, a back of the book problem or something like that as you're practicing these, it will probably pull one of these out and leave. So it pulls, there's 3 of them, right? It took 3 of them and pulled 1 out, and it would leave the 3 minus 4x squared underneath, and then plus c. So either of those two versions would be where we would stop. Okay, so far so good. It's the first one we've really done, outside of the setup one. Now, number 2 looks a little different because there's division. It's not a product, right? And one of the things that we started with in this whole section was saying, hey, things are going to look like products. So how could I rewrite this so that it doesn't look like a quotient, but instead it looks like a product? Yeah, so what's in the denominator? I'll just write it first. I could write in the numerator with a power negative 2. Okay, is that all right with everybody? We don't have a quotient rule for antiderivatives anyway, so that's really not what we would want it to be written as, even if it were simplifiable as it was, right? We would definitely want to shift things up. Okay, so do you see something that looks like an inside function, and if so, what is it? Yeah, this is 1 plus x to the 4th. So I've got 1 plus x to the 4th. What is the derivative of 1 plus x to the fourth? Not quite. 4x cubed dx. Now, there's a minor problem, and it is very minor, in that this has x cubed dx, and we're supposed to be having 4x cubed dx, right? So here's how we solve that minor problem. We simply divide the 4, or write the 1/4 to the other side. Okay? So what this really says now is that I'm going to be replacing the x cubed dx with 1/4 du. That's what it says. So over here, as I'm rewriting, I have my integral. I have the part that's in blue, which is now my u to the -2. And then at the end, I have a 1/4 du. Okay, it's a very minor problem when there's a coefficient issue. We simply shift it to the other side. What's even more is that 1/4 is just a constant multiplier, and most of you have gotten really good, at least on your gateways, at recognizing that constant multipliers don't change anything, just like they didn't with derivatives, right? They just come along for the ride. They just stick with what's ever next. So this 1/4 doesn't actually end up affecting anything, so if you want to think about it as being sort of out in front or at the beginning of the u squared, so either right there or right here, like that, you can do that, whichever of those versions you like. I'll go with this one since I just wrote it. The 1/4 just will stay. What is the antiderivative of u to the -2? Good. U to the -1 over -1. Do remember your plus c's. All right, so this negative can go in front of the 1/4, and the u to the -1 can go in the denominator. So this can be -1 over 4u plus c. That would be the simplest way I'd write it in terms of u. And then I need to make sure that I do what? Plug back in for u. I got to get the u out and put the x back in. So it's always identified up here, so you know exactly what it is. So this is -1 over, the 4 can stay in front of it, doesn't need to be multiplied through, 1 plus x to the 4th plus c. Any questions? Okay. Let's do it with some trig. Square which part?
So like originally it was 1 plus x to the 4th squared.
Yeah, so the squared went away right here when I took the antiderivative in this step. I added 1 to the exponent, so the exponent did in fact change, and it would stay changed in the final answer. Yep. Okay. Trig functions. Do you see a product? Yes. What would be my inside function? X to the 4th. It's the thing that's stuck inside a sign. Okay? So as you're looking at these, you've got two pieces that you're considering. And what you're always wanting to ask yourself is what's stuck inside of another function? What's an inside or a composite function that's here? And that would be my x to the 4th here. So my u is x to the 4th. So then what is my derivative of that? 4x cubed dx. So while it's not written in sort of the same format, my 4x cubed dx, which is at the beginning and at the end, is going to be replaced by the du. Sign is going to stay. And then my x to the 4th is my u. So I have the antiderivative of sine of u du. What's the antiderivative of sine? Good. Negative cosine of u plus c. And then replace my u. So it's negative cosine x to the 4th plus c. Is it good? Okay, so it's your lucky day. We're going to get 2 trig ones right in a row. I know, it's very exciting. Okay, so again, this looks like we have division, and I don't want division present. The difference is that there might be more than one way to deal with the division, right? So one option might be to pull it up, and we might not choose the right option to begin with. Another option might be that because the cosine's in the denominator, we replace it with some reciprocal identity from trig. Okay, so we have some options here. However, what I would like you to recognize is that sine and cosine are each other's derivatives, right? So if we bring this up, it works really nicely. And the reason is because this is the cosine of x, and it would have been cubed in the denominator, so it's -3 in the numerator. And we have the sine of x, whoops. And the reason this one's actually really nice is because sine's derivative is cosine, and vice versa, with a negative maybe attached to one or the other, right? Like there's a negative attached to some of them, but they're pretty much each other's antiderivatives and derivatives. We can go back and forth very easily. So having one of them be an inside function and the other one being its derivative is very friendly in this particular setup. So in fact, while I do have some quotient identities, the simplest way to do this is still with use substitution and pulling it up. Because my embedded inside function is now the cosine of x, right? So that's my u. U is cosine of x. So then, what is my derivative of u? This one does have the negative, so negative sine of x dx. But I don't have negative sine of x dx, I just have sine of x dx, so what do I need to do? I'll just pull the negative to the other side, right? So it's negative du that will replace my sine of x dx. So over here, I have an antiderivative, and I have, well, I'll do it in order. I have u to the -3rd, and then I have negative du. But I'm going to put my negative in front. So I have the antiderivative of negative u to the -3rd du. You don't have to show this step. That would definitely be optional. But if it helps you to keep all the pieces, then do it. What is the antiderivative of negative u to the -3rd? Good. And then plus c. Excellent. Okay, so we got lots of negatives. So the negative here is happening simply because it's there. And then I have u, is it u to the -3rd? I'm actually glad that you did it because some of you are making that mistake on your gateway. Be careful when we're doing things with negatives because they work the same, but the process kind of thinks through a little bit differently with negatives. So it is u to the -2. Okay, I've got double negatives, so we've got these now positive. And I've got u squared, so I'm going to put 1 over 2u squared now in the denominator. And what is u? Cosine of x, so this is 1 over 2. You can either write it as cosine of x squared like that, that's fine. Or you can write it cosine squared of x like that. Your favorite. You get to go with it. Okay, any questions? Okay, so the directions are going to change slightly. We're going to be doing a little bit different things with these now. This one actually wants us to find an equation for the function that has the given derivative and whose graph passes through the given point. Now we've had these directions before. What this is really asking me to do is they're asking me to find the c at the end. That's what it's asking me to do, is find c. So I'm asked to find the function that has this as its derivative, which means it's wanting me to do an antiderivative of my problem. Okay, this ending point right here we'll need in a moment. But it's wanting me to find the antiderivative of the secant squared of 2x dx. Now, this one's a little bit different. And the reason it's a little bit different is for this section anyways, because it doesn't look like there's a product, right? But do you see the inside function? What's the inside function?
2x.
It's 2x. And the derivative of 2x is what? 2. So while this one doesn't look like there's a product, it's because the derivative that we get is simply a constant. And constants don't actually have a lot of problems being fixed within a problem. We did one right that way already. This one over here, right? It had the 4 that was messed up. This one had a negative that was messed up. A constant doesn't cause things to sort of go awry. What ends up happening is we just get them divided out on the outside. So the fact is that this one is a product rule. It's just it's a really simple product rule. I mean, not product rule, but it's a really simple integration rule. So we have this 2 dx. And like I said, there's no 2, so I need to make it to the other side as a 1/2. So my antiderivative will be taken of the secant squared of u du with a 1/2. Put it here if you wish, or put it at the beginning. It doesn't matter. So there's a 1/2. What's the antiderivative of secant squared? Tangent. Some of you are still brushing up on those, I know. Tangent of u plus c, right? Now what? Substitute in the u. So this is 1/2 tangent of 2x plus c. And on the left side, I didn't really do anything, but when I take the antiderivative of f prime, I get f of x, right? That's what the antiderivative of f prime would be if I go backwards. And then what I'm asked to do at the end of this problem is to take this with that ordered pair I'm given, pi over 2 and 2, and I'm trying to figure out what c is. So f of x is the 2, it's the y value, and then the x value is pi over 2, so this is 2 times pi over 2 plus c. So obviously 2 times pi over 2 is pi. What is the tangent of pi?
0.
It's 0. So this whole thing is 0, which means my constant is 2. So c is 2. So the solution that I'm looking for is that f of x is equal to 1/2 tangent of 2x plus 2. It is a specific antiderivative because I found c. Okay, so 6 is a truly weird one. Are you ready? First, does it look like a product? Yes. Okay. But it's weird, and let me show you why. What's the inside function if you were trying to pick one? Yeah, it looks like the 2 minus x, right? For sure. So u is equal to 2 minus x. But the problem is, what's the derivative of 2 minus x? Negative 1, or just negative dx. And that is definitely not what's on the outside. There's an x on the outside. Okay, this is not the same that we've done before. This is a uniquely different type of problem. But there's nothing that we've done that's wrong so far. Here's the way we fix this particular problem. So there's an x on the outside. That's not ideal. I'm trying to put everything in terms of u, correct? So let's rewrite this equation solved for x. If u is equal to 2 minus x, what is x equal to? What is it? It is, I think it's u, I think it's 2 minus u. 2 minus u, I think. Agreed? If we shifted things twice or whatever. Yeah, 2 minus u. So as I do my substitution here, part of you are going to be, part of the inside of you is going to be thinking, I don't see how that helps anything at all. Okay, I totally get that feeling. Just bear with me for a second and I'll show you how. So I'm replacing the x with 2 minus u. And then I have the plus 1 on the outside. So all of that comes before the square root. And then I have the square root of u. And then I need to get a negative involved, right? Because there's the negative 1 there that's got to shift to the other side. So I'm going to have a negative. I'm just going to put it in the very front so I don't have to look at it too much. And at the end I have du. So the reason it probably feels like, or if you haven't recognized why it should, that this is not particularly helpful is because it still looks like a product. Doesn't it? I know there's kind of a mess we can clean up on the outside. In particular, this is really just 3 minus u. But now I have 3 minus u. And then I have the square root of u du. Or if you want to distribute that negative through, you could write this as u minus 3. It's a little bit friendlier since my u would then be positive for purposes of derivatives and antiderivatives. And it doesn't feel like we've made any progress. But we really have, and here's why. Having addition and subtraction on the outside of a radical is far superior, that is, it's easier to work with, than having it underneath the radical. Okay, and let me show you why. I can actually distribute the addition and subtraction when it's outside of the radical. I can't distribute when it's underneath the radical. So this problem becomes the integral of u, well, it's u squared u, we'll combine it in a minute, minus 3 squared u du. There's no more product. That's really what happens, is because I'm able to distribute when subtraction or addition is outside of the radical, and I'm not able to distribute when it's underneath the radical. So u squared of u is the same thing as u to the 3 halves, right? U to the 1 and u to the half is u to the 1 1/2 or 3 halves. And then 3u to the 1/2 du. And we can take that antiderivative, yes? Sure can. So what's the antiderivative of u to the 3 halves? U to the 5 halves over 5 halves. And how about the 3u to the 1/2? Good. 3u to the 3 over 2 divided by 3 halves plus my c. We'll clean things up a tiny bit. So I have 5 halves like this. And then I have this, I'm going to do it a little bit at a time, square root of u to the 5th. And then I have minus, so I have 3 times 2/3, which makes it just 2. So when I multiply or divide by that, I get just 2. And then I have the square root of u cubed plus c. Okay, that's that, or pulling the u's out is the cleanest version with the u's in it.
Wouldn't it be 2 over 5, not 5 over 2?
Yeah, the first one.
Oh, yes, it should. Thank you. Got it on one, not the other. Cool. All right, so as we clean this up, we'll be finishing up on this problem. I think that means I have a tiny bit left to post a video for. But I'd like to show you how this cleans up, because it cleans up in a little unexpected way. So I actually am going to pull those u pieces out for a moment here. So I've got 2/5, and I have u squared, and then square root of u, and then minus 2u square root of u plus my c. I do need the u plugged back in as 2 minus x. So I have 2/5, 2 minus x squared, square root of 2 minus x, minus 2 times 2 minus x. Oh my goodness, running out of space. Times the square root of 2 minus x plus c. Notice that they both have a square root of 2 minus x in them. Okay, so if I were cleaning this up to its like cleanest potential, and I'm not saying this because I really care. If you left it at this point, something like this, I'm all right with that. But I want you to recognize, if you were looking at some additional problems, or you're looking at like a calc chat where they actually simplify things fully and cleanly, and you're like, whoa, what the heck? You know what happened, okay? So if you pull out a square root of 2 minus x like that, you're left with the 2/5, and then these pieces can actually be multiplied out. So if I take 2 minus x squared, I'd have 4 minus 4x plus x squared. And over here, if I multiply my 2 through, I would have minus 4 plus 2x, like so, plus my c. I think I need to close one more parenthesis maybe. No, I did it. Plus my c. If you don't like the 2/5, we can pull that one out too. That one works pretty nicely to be pulled out. I think I did that on my paper. No, I didn't. Oh, isn't that fun?
You should also factor out the 2 minus the x.
You could. Yeah, you could from their point. That might be a little bit cleaner. Let me go back and do that. So just draw a line through that if you just did that. Let's do that because I like that idea too. So you can have a 2 minus the square root of x. Minus x and the square root of 2 minus x. And then you'd have the 2/5. Yeah, that's a little bit cleaner. 2 minus x. And then over here you'd have minus the 2. Yeah, that'll happen a lot faster than thanks, Jewel. And then you would be cleaning up the pieces that are left, I think.
Why is it square root of 2x minus 5?
Why is it the square root of 2x minus 5?
Should I just?
Here, I left my, because I just wrote it down. Time is of the essence. We're running out of it. I'm trying to hurry really fast and making mistakes. That's why. All right, so I'll pause there. But this piece we would simplify, right? You just merge the pieces together, do a little bit of simple cleaning up of algebra, and it'd be another version of your answer. That one could show up. So I will post a video for the last, I think it's two problems, so that you can see what they look like. In particular, it's very important that you watch them. Here's why. The last two problems are definite integrals. They tell you what happens and how the use substitution affects things when there's numbers on top and bottom. I haven't talked about that at all, and it's not necessarily what you might think it is, okay? So be sure and watch those last two videos. When I post it, I'll tell you where to start the video for the second one, all right? Have a good week, guys.